So what can we do to compare two different algorithms that solve the same problem? For instance, we are faced with the task of measuring somehow the magnitude of the complexity of algorithms in terms of time efficiency. But how can we give a measure in order to compare these two programs that compute both a Fibonacci number? The first approach would be to measure the time of the competing programs. We execute the programs and measure the execution time. But this is really not a good idea, because we cannot compare the execution time for all possible inputs. The number of different input values is too large to check them all out. The second problem with this approach is that the execution of programs depends on the underlying hardware. So our measure is not the pure measure of the complexity of the algorithm. The third problem is that we need to implement the algorithms. We would like to have a more abstract measure of the complexity of an algorithm, independent from programming languages. So let's try to find another measure that is more abstract and also easier to obtain. So how to measure complexity? To each algorithm, we'll assign a function f of some value n, where n is a measure of the size of the input. N can be the argument itself, the value, or is in this example the length of an array. In this case, an array we want to sort. This function f represents an abstract measure of the complexity of the algorithm. But let's concentrate on sorting. The time we take to sort an array of length n might depend on how sorted it is to start with. An array that is already sorted probably takes less time to sort than an array that is very unsorted. Well, in this case, we'll take the worst case as the representation of the complexity of the algorithm. Further, we will consider the asymptotic case. With this we mean that we observe the behavior of the program, of the algorithm, when the value n tends to infinity. In the sorting example, n is the size of the array to sort, so we want to see the behavior when n is very large. Then what we're going to do is to count how many operations we execute. We know that in reality not all operations take the same time. But we make a simplification here, and we will assume that all operations take the same time. These operations, in a very comprehensive understanding, include such things as assignment, the call of a method, or returning from a method, any kind of arithmetic operation, and indexing of an array, etc. Let's see a very simple example in order to understand better what we're talking about. Imagine that you are given an array and want to find its highest value now. The method takes as input an integer array. But for the method to work, the array has to have at least one element. Its length has to be at least 1. You might implement this precondition with an exception, an if statement, an set statement, or whatever. This is not relevant here. So if we know that there is at least one element, a of 0 exists, and we might save its value in a variable m. M shall hold the maximum value seen so far. And since we have only seen one value, this is also the maximum value seen so far. Then we traverse the array from position 1, the second, to position n-1, to the last one. Therefore, the loop is executed n-1 times. Each time we compare a of I with the maximum value seen so far, m. So if a of I is larger than m, this a of I shall be the new maximum value seen so far and assign it to m. Otherwise, we don't do anything. Otherwise, there's no change for m. And once we have traversed the whole array, we return m, as it is the maximum value seen so far after having expected all the values in the array. So what is the number of operations we have? In order to be able to count, we have to make some assumptions about the input array. We will consider two extreme situations. The first one is when the maximum value is already at position 0. This means that once m gets initialized at the beginning, it gets never updated again. This means that the assignment statement in the conditional never gets executed. So how many operations do we have? Well, let's count. 2 for the initial assignment of m, where there's also an access of an array. 1 for the initialization of counter I. Then the termination condition has to be checked n times. n minus 1 times we enter the loop, and 1 we don't. I is incremented in n minus 1 occasions. So 2 times n minus 1, because we have to increment I and assign it to it. And then we have to check the conditional n minus 1 times. The condition implies 2 operations, 1 for accessing the array and 1 for the check. So 2 times n minus 1. And finally return m, which means another operation. So altogether it is 5 times n. Now we do the same exercise with another extreme case. Here the array is in ascending order. So each time we advance with the loop through the array, we encounter a number that is larger than the ones before. So we always have to update m in the conditional. So the counting differs from the one before in that we have to add 2 times n minus 1 for the assignment statement, which is always executed. Now the final result is 7 times n minus 3. Now between the two extreme cases, we might have others where the statement is executed sometimes and sometimes not. So in general, the number of operations will be between 5n and 7 times n minus 3. But we will simplify even further and say that the complexity of this algorithm is of the order of n, meaning that it is a polynomial of n with 1 as highest exponent. We forget about the constant terms like minus 3 and also about the coefficient 5 or 7 or something in between. This proportionality of n gives us enough information about the algorithm. We know that when we duplicate the length of the array, the time to compute its maximum will also roughly duplicate. So in this video we have set the principle to find an easy way to compute the time complexity of an algorithm. One that is not too difficult to calculate, but is sufficiently abstract and gives us enough information about the asymptotic behavior of the algorithm.